All right, so in this one, well, to tell you the truth, you guys have done related rates before, haven't you? You guys liked it the first time around? Remember what those were? That was like the ladder falling type of a question. Did the cars come to an intersection type of a question? Like how fast were they like getting closer together as they approached the intersection or moving away? That type of thing. So now with trigonometry, we're gonna say like as the angle is changing, right? So now instead of a change of rate of a distance, we're gonna have a change of rate of the angle. Okay. So then we're gonna have to be throwing in like tan and cos and everything else, right? So a little bit of a review on this one. You guys will need to use, well, SOHCAHTOA, and then it could be sine law or cosine law will show up. So, yeah. You guys remember those, right? It's fine. It's really just the equation. We'll do this one. You know what? Everything you guys have done now, you guys are gonna be like, it's easy, right? You just kind of plug the numbers in. It's pretty straightforward. Yeah. Okay. So for the first one here, it says two sides of a triangle have lengths 15 and 20. The angle between them is increasing at pi over 90 radians per second. How fast is the length of the third side changing when the angle between the sides is pi over 3? And then give your answer as an exact value. All right. So what does all that mean? So really, you guys are going to want to draw a picture every time. So let's draw a picture of a triangle. Okay. So then this will be my angle. You guys see that, right? Yeah. And one side is 15 and the other side is 20. So now it's asking how fast is the length of the third side changing when the angle between them is pi over 3, right? So it's really this. And we want to know how fast, so as that's growing apart, right? We want to know how fast this distance from here to here is growing at a certain angle. So you guys kind of remember that before, how we have to figure out with our constraints what the values are given those constraints at that like snapshot in time. It's pretty much how these things are working is you've got like this angle changing, right? And then if you could take a picture at a specific moment, right? It's like take a snapshot at that certain time. Then the question is how fast is that length right there actually changing? So we're gonna have to like take a picture on these questions, right, to kind of figure out what all the
This one's going to be when the angle is power 3, right?
Yeah, when the angle is pi over 3, yeah. Yeah, exactly. So once it gets to that point of pi over 3, how fast is the distance between those two things changing? Yeah? Okay. All right. So in order to do that, well, which one are we going to use? Do you guys remember looking at this picture, whether or not that would be, well, SOHCAHTOA, sine law, or cosine law? You guys remember from Math 20-1?
You have two sides and an x. It's one or the other. I know that.
Yeah. Well, so really, the way I would do it is we know it's not going to be SOHCAHTOA because it's not a right angle, right? Mm-hmm. So it's going to be sine law or cosine law. And really, I usually use sine law whenever I can, unless it's either a case where you have side, angle, side, which is what we have going on, right? Like an angle sandwich between there. That would be cos law. And then the other one is side, side, side. If you have all sides, then you have to use cosine law as well. Other than that, you'd be using sine law.
Is that on a formula sheet too, sine and cosine?
I can't remember, but if it's not, then I would just give it in the question. Yeah, I won't make you guys memorize those. Yeah. Okay, so we're going to use cosine law. So let's write that up. So we need to. So first off, though, yeah, we need to find x. We need to find what the length of x is when we're actually at pi over 3. So that's going to be like our snapshot in time. We'll figure out what the value of x is. So we'll write it out as x squared is equal to, and then it would be 15 squared plus 20 squared minus 2 times 15 times 20 times cos theta. Okay. So yeah, do you guys see where we got this from? This is just cosine law, and I'm just filling in the numbers there. Yeah, okay, all right. So let's simplify that up a little bit. So that'd be x squared is equal to, and that would be 625 minus 600 And then it would be cosine of, and then what would I actually put in for my angle now?
Power 3.
Yeah, pi over 3, because this is like our snapshot in time, right? We're able to actually put that number in. So that's the angle that we're wondering about. So simplifying a bit more, we've got x squared is equal to 625 minus 600. And then what is cos of pi over 3? So it's like the x value on the unit circle when you're right before 90, right? That's the one before 90.
I'd say that's.
It's either a half or root 3 over 2.
Half.
It's a half, yeah.
I was forgetting if a half is bigger or smaller.
Yeah. I know what you mean. Yeah. Okay, so okay, so then x squared is equal to 325. So x is equal to the square root of 325. And then if you split that up, that would be 25 times 13. So then we could rewrite that as 5 root 13. All right, so we're going to need that in a second. All right, so yeah, what do we know? So we know d, let's say d theta dt. What's that equal to? Yeah, in the context of my question, what was that?
Pi over 90.
Yeah, it's pi over 90, right? This is my, how fast my angle is changing every second, right? So that's pi over 90. Okay, so we got that one. We know the angle is going to be pi over 3 at that moment, right? We know x now. X was, what was that, 5 root 13? And what else? And then the one we're looking for, what would we be looking for? It says how fast is the length of the third side changing? So what would that look like? That would be, what's that? Yeah, exactly. That'd be dx dt. How fast is the length changing with respect to time? Okay, so that's the one we're after. All right, so now we're going to take the derivative of something, right? You guys are probably expecting this. What should we take the derivative of? What should we do here? Like an equation, you guys?
I mean, we need an equation that relates all the values.
Yeah, exactly.
Derive the cosine law equation.
Yeah, let's actually just use the cosine law again, but I'm not going to throw in a value for theta, right? Because this is a changing value, right? This is like in the general equation for as the angle's changing, right? So we got to leave that as just theta. I can't throw in that number. Like I was here, I was able to throw in pi over 3 here because that was our snapshot. That was our picture in time of that. So let's just write out really this again without the pi over 3. So
Are we going to put the pi over 3 in at the end after we take the derivative?
we will need it in the, after we take the derivative. Yeah, exactly. Yeah, so there's to be x squared is equal to 625 minus 600 and then cosine theta. And now we got to take the derivative of this. Okay, so taking the derivative of this would be 2x. And then what?
600 sine.
Well, so remember what we're doing here when
Times x prime. Wait, what?
yeah, right it is times x prime. But we like doing it in Leibniz notation, like with the dx dt, yeah, so it's with respect to time. So it'll be the derivative of x with respect to time. And that's perfect because remember that was what we were looking for. How fast is the side length changing? So good. So we that's actually a good thing that happened. Is equal to derivative of 625 is 0, so that's gone. And then that'd be minus 600. And then the derivative of cos is
Plus 600 sine.
yeah, you're ahead of me. So negative sine theta. Okay. Anything else? Yeah. Yeah, exactly, because we kind of have to do like chain rule here, right? We took the derivative of sine, and now you got to take the derivative of theta, but it's the derivative of theta with respect to time, right? So d theta dt. So just don't forget about those. That's an easy place to make a mistake, right? To forget to tack those on. So this would be, yeah, we can actually put the numbers in now. So this would be 2, and then instead of an x, what am I putting in there? Yep, 5 root 13. And then dx dt is what we're after. Is equal to positive 600. And then now we're okay to put pi over 3 in there, right? Because it's at that moment. So pi over 3. And then d theta dt, or what would that be? Pi over 90, yeah. There you go. Okay, so dx dt.
I always mess up this stage.
Well, I'm not really going to do anything fancy here. I'll just simplify the...
Select all the terms, and then like you end up with like radicals and pies and stuff.
I always end up doing something wrong or something. But I'm also
Well,
not
heck, you
techie enough
have to
to
run
run
my calculator.
some kind of impact.
Yeah, tell you guys the truth on this one, you know, that would pretty much be our answer. We could simplify that up a lot better. I'm going to get a little lazy here, though. Let's say this is approximately equal to 0.50 meters per second.
It's like we're learning about it, and it's kind of hard to understand. Like some world we live in.
Yeah. All right, next one.
Elon Musk, smarter than Einstein.
Nah, he just kind of fools the stuff.
All right. So, classic example, we have a beacon located on a perpendicular, or at a perpendicular distance 315 meters from point R on a straight shoreline, revolves at 1 revolution per minute. And then how fast does the beam sweep along the shore at a point 420 meters from R, and then round to the whole number and convert. Okay, we need a picture here. Okay, so let's say there's my lighthouse. Okay. Okay, so if it's 350 meters from point R, so this would be 315 meters. From here to here, this will be point R. Okay, and then down the shoreline would be S. Okay, so this is like my shore from R to S. That's actually like the shoreline there. And you can imagine we'd have this angle that's going to be sweeping across the shore. So this length from here to here is going to be changing. You guys see that? Yeah? Okay. All right, so that's 315. We're going to call this side Y. Now, I'm going to do this one a little bit different because on the last one, I kind of helped you guys find, you know, that snapshot in time to find X, and then we ended up using that X to find or like in the derivative after. Sometimes, like, if you don't know where to get started, you can take the derivative and then kind of figure out what it is that you needed. What you needed. Yeah, like sometimes I find that easier. I'm like, oh, okay, I needed that. So let's go at it from that angle this time. So let's say, okay, tan theta is equal to, and what would tan theta be equal to? Yeah, y over 315. And that's probably good, right? That relates our angle and our distance that we're interested in here, right? So that's kind of a good place to start. So that's going to be the thing that we want to take the derivative of. So let's see what we get when we do that. So here, I'll move the 315 up here first. So we get 315 times tan theta is equal to y. Okay. Now, taking the derivative of this, we would get 315. Here, I'll do a different color here. 315. And then the derivative of tan theta, what's that again?
Just give me 1 second. Off the top of my head, isn't it? Secant squared.
Oh, man.
Good job. Well, actually, you're only half right.
Secant squared. Theta times tan.
Times tan. How can tan be the derivative of tan?
So somebody else. Yeah, it's with respect to time. So d theta dt.
Never mind, not this one, the sum.
Right, so it's like the derivative of the inside there. So d theta dt is equal to, and then the derivative of y would be 1, and then that would be dy dt.
Tyson loves visualization.
Oh,
He said it himself.
Yeah, I did.
Which is it?
Is it Lieb or Live?
Leibniz.
My bad, I'm sorry.
Okay, so then from here, we can see, you know, what the things were that we needed here. So secant squared theta. Okay, that seems like I must have needed theta at that point in time. I needed d theta dt. Okay, do I have that one? No, not quite. And then dy dt, and that's good because dy dt, that's actually what I'm looking for, right? How fast does the beam sweep along the shoreline at 425 meters, right? Okay, so what do you guys think we got to do here then? We need to solve for some things here.
We need to solve for theta and the derivative of theta.
Yeah, and you know what? Let's figure out d theta dt first. So d theta dt is equal to, and then what do you think that relates to in our question? It's gonna be for time, isn't it? How about that one? 1 revolution per minute, right? That's probably going to be how fast our angle is changing over time, right? But you guys are right to be a little confused, right?
Well, it's 360 degrees.
Yeah, that's right. So you can think about, so 1 revolution, you can think about, yeah, so 1 rev per minute. How much would 1 revolution be on the unit circle if you were, yeah, in radians would be 2 pi. So 1 revolution is 2 pi. And then the next one that we're going to do, it says convert to meters per second. That's really this step. All we have to do is make sure our units are all consistent. So if these are in meters and I want to go meters per second, then I'm going to change this into revolutions per second. So how many seconds are in a minute?
Up to you.
60, right? Okay, so it's pi over 30. All right. Now, we also know if we're solving for the angle, right, at this snapshot, well, right at that snapshot, we also know that the length is 425 meters.
Then you can solve for theta.
Yeah, then we should be able to solve for theta, right? So theta, here I'll just write a little equation there. That'd be tan theta, it'd be equal to 425 over 315.
Wait, so where'd the 2 pi over 60?
So 1 revolution, right, on the unit circle is 2 pi.
Oh, okay, right.
So that's all it is. So I just replaced 1 revolution with 2 pi.
Yeah.
Yeah, and then 60 was just to change it to seconds, because 1 minute is 60 seconds. Okay, so back to this one, it'd be theta is equal to, and that'd be tan -1 of 425 over 315. Now, if you were asked to leave your answer as an exact value, you would just leave this, right? You wouldn't actually convert this to a decimal at this point, right? Which gets a little bit messy sometimes if you have to have these like, inverse tans and everything in your answer. We're just gonna round it for now. So this would be approximately equal to 0.933. All right, and I think we got everything we need, right? Or what do you guys think? We got theta, that's what we just solved for. We got d theta dt. We're good to go. So that'd be, 315 times secant squared of, and then 0.933, and then times pi over 30. Is dy dt. So that's equal to, so you guys could, like with your TI Inspires, you could put that right in, but that'd be the same thing as 1 over cos squared theta too. You put that in that way. But in the end, we would get 93 meters per second. All right, part B. How fast does the beam sweep along the shore at its nearest point R? Okay, so in this case, you've got your lighthouse, and we've got R. So we're saying actually like when it's straight across, so if this was still our, S over here, then we're making like a tiny little triangle, or like a more acute triangle. And you can picture this thing right as it passes through this point here, through this point here, right? Where this would be our Y, let's say, and our angle would be in here. So like even smaller than that, we're gonna go right down to an angle of 0, right? So what do we know here though? We know, well, d theta dt, do we know that one? Yeah, that was from the last question, right? That's consistently how fast the angle is changing, right? So that's gonna be pi over 30 still. What would our Y be?
0?
Yeah, it's actually 0 there. Right when you're right at that point. And then the angle? Also 0. Okay. So then, again, we could just go to our equation that we had here, right after we derived. So 315 secant squared theta. And then d theta dt. Okay, and then we can just kind of fill in what we know. So this would be 315. And then secant squared theta, I'm just going to write this as 1 over cos squared of, and then I could put the angle of 0 in. So what is cos of 0 degrees? 1, right? So this is really just going to be 1 over 1. So this whole thing is just 1. Nice. And then that was pi over 30. This is equal to dy dt. Okay, so in the end we get 21 pi over 2 meters per second. All right, last one. All right, As the sun rises, the shadow cast by a 15-meter tree is decreasing at a rate of 55 centimeters per hour. At what rate is the angle of elevation from the shadow to the sun increasing when the shadow is 15 meters in length? Give your answer as an exact value. All right, so first thing we got to do, we got to draw a picture here, right? So if we got a tree, so obviously it needs to be green.
Good thing this is not.
Okay, so then you've got the sun, which I nailed. Yeah. All right, so here's our angle. We know our tree is 15 meters tall. And it's saying at what rate is the angle of elevation? So really we want to know d theta dt. At what rate is the angle changing? All right, so what else do we know here? So ds dt, do we know that one? Oh, sorry, I don't have an S drawn. This would be my shadow. That'd be my S from here to here.
We know the rate that the shadow is decreasing.
Right, so what would that be?
ds
So ds dt would be,
negative 55.
hey, you guys nailed a negative 55 centimeters per hour. Okay, so now the other little issue we have here though is that this is in centimeters per hour. Just be careful because it's saying meters and meters.
Centimeters per hour? Are you kidding me? Who's measuring that?
So what we should probably do, let's just change this into meters per hour right away. So negative 0.55 meters per hour.
Yeah, well, the metric system.
Okay, we know S is 15 meters. But S is 15 meters at that snapshot in time again, right? So it's not always 15 minutes when we're doing this, but is that right at that moment? All right, so if we want to figure this one out, we could do the same thing again, right? You could say, okay, let's just take the derivative of this thing and then see what we need after if we want to. So it could be tan of the angle is equal to, what would it be equal to as our original equation? How do I relate the angle, that side, and S?
So for tan,
Yeah, exactly. So just be tan theta is equal to 15 over S. Okay, so that should be good. What would you guys do now if we're going to take the derivative of this? Take the derivative? Yeah, one thing I'm going to do first, though, let's write this one more time, is tan theta is equal to 15, and then times S to the negative 1, just to get it ready. Okay, so derivative of tan is secant squared theta times, yeah, d theta dt. And then this would be negative 15. And then you guys all right if I write this as S squared? Skip a step there. And then times, what'd you say it was? Yeah, ds dt. Okay, so what do we have and what do we need here? So we're looking for this one, right? So that's good. We're looking for d theta dt. It looks like we need the angle at that moment in time. Yeah. And it looks like we need S. And we actually have S, don't we?
Yes.
And we have ds dt. So I think all we have to do is just find the angle at that snapshot in time. So at that snapshot in time, what was S? 15. So we could make a little, we could figure out the angle at that time, right? So we could write it out as tan theta is equal to, well, that would be 15 over 15. So where is tan theta equal to 1? Yeah. Pi over 4, right? Because it's root 2 over root 2. Or root 2 over 2 over root 2 over 2. Yeah.
And then it'd be 5 pi over 4 too.
Yeah, but we're going to stay in the first quadrant for this one, yeah. Yeah. Okay, so we're good to go now. So let's plug it in. So you'd have, I'm going to rewrite secant squared as 1, secant squared theta as 1 over cos. 1 over cos pi over 4 squared times d theta dt is equal to, and then that would be negative 15 over, and then s was 15 squared, or s squared was 15 squared, and then ds dt was negative 0.55. Okay. So d theta dt is equal to, and now all of that stuff, if we want to look at the exact answer, how would you guys do that?
Negative 1 over 15. Technically 15 over 15 squared.
Right, so you can simplify that one, and then there's negative 0.55, that'd be like 55 over 100.
It's like 11 over 20.
Yeah, so you can simplify it all that way, but you know the way I would probably do it if I was you guys? Put in your calculator, push math, fraction.
Right. I don't
Yeah.
trust that.
Yeah, so if you want to, you end up getting 11 over 300.
He said, well, we're kind of math easy.
And then times cos pi over 4 squared. I just brought the cos pi over 4 squared from the bottom to the top there.
Why was S negative 15 over 15 squared?
So it was negative 15. That was just from taking the derivative here, right? The negative 15. That just came from taking the derivative.
Right.
And then the s squared was just in the bottom. And then s we just knew at that moment in time was,
Ended up being
yeah, it's because they were both 15. Yeah.
That's right. That's
Yeah.
right. When you first drew that picture, I thought it was going to be like a double triangle question.
Hmm.
You have to do all of that stuff.
All right. So what would cos pi over 4 squared be? Actually, let's write that out. Like, what would cos pi over 4 be? Or, yeah, cos pi over 4. Yeah, root 2 over 2. And then squared.
That's just
So that'd be 11 over 300 times 2 over 4.
1 over 2. Yeah.
Yeah, it is 1 over 2. Don't be hard on yourself.
You gotta try this.
Okay. I'm going to cancel that. Call that 1. Call that 150. So we get 11 over 600. Oh, and we should write down that's radians per hour.